In this video, we're building a powerful deep learning model that can analyze images of skin lesions and classify them as either benign, aka non-cancerous, or malignant, aka cancerous. Now this kind of classification can assist dermatologists in early detection of melanoma, a deadly form of skin cancer. Now we'll be using Inception v3, a cutting-edge convolutional neural network pre-trained on ImageNet, and fine-tuning it on our own dataset of over 10,000 images. Now we're also going to be using TensorFlow during this project. So let's get started. Alright, so the first thing we're going to need to do is find our dataset, and you can go ahead and search up Kaggle.com, a resource that has tons of machine learning datasets for free download. So we're going to search up over here, skin cancer. Then we're going to click datasets and scroll down until we see melanoma skin cancer dataset of 10,000 images. Now if we scroll down, we see that we have two subfolders, test and train, and we have two classes, benign and malignant. So we're going to go over here and download this dataset. Now make sure that you have an account, as that is needed in order to download it. Okay, so now we're going to go over here and click runtime. Then we're going to click change runtime type, and we're going to change it from the CPU to the T4 GPU. And the reason for this is because the CPU is extremely slow when it comes to machine learning tasks, and you want to use the T4 GPU just to speed up the process. So now you're going to click save. And so now what we're going to do is install and import our dependencies. First, we are going to be importing TensorFlow as TF. And so TensorFlow is the heart of our deep learning model. It provides all the tools to build, train, and deploy neural networks. Next up, we are going to be importing OS. Now, OS is used to interact with the file system, and we're going to use this to change directories and list files. Okay, so next we are going to be importing image header. And so image header is used to confirm that the files are valid images, which helps avoid errors during training. Next, we are going to be importing NumPy as NP. And so NumPy is essential for numerical operations and array manipulation. Okay, next from matplotlib, we are going to be importing pyplot as PLT. And so matplotlib is great to visualize training performance or show image samples. And then finally, we are going to import pandas as PD. And pandas is great for analyzing structured data. And so we're going to go over here and run this cell. Alright, so next up we are going to have to upload our dataset to Google Colab. So I'm going to say from google.colab import files. Then I'm going to say train underscore dataset is equal to files.upload open and close parentheses. Now basically what this means is that I am going to be uploading my train subfolder as a zip file because I compressed it, and then I'm going to be saying that equal to train dataset. So whenever we reference it later on, I'm going to be using train dataset. And then I'm going to be unzipping this file within Google Colab, which is necessary. Okay, so you can go ahead and run the cell and then choose your train.zip file. Okay, so once the cell finishes running, I'm going to copy and paste, and I'm going to call this instead test underscore dataset. Now I'm going to be unzipping the test.zip. We're going to run it like before, but this time I'm going to be uploading my test.zip. Okay, so now that we have our data loaded on Google Colab, I'm going to create a new code cell. And now we're going to pre-process with image data generator. So I'm going to say from TensorFlow.Keras.preprocessing.image, I am going to be importing image data generator. Then I'm going to copy this, and I'm going to say train gen is equal to paste parentheses 1.255. Then I'm going to copy this and paste it again. But this time I'm going to change the train to test. So basically, what are we doing in this cell? Well, basically, our images, the pixel values for our images, range from 0 to 255. And so we're rescaling them to 0 to 1. And the way we do this is using image data generator and then parentheses 1.255. Now the reason we do this is because it standardizes the input, it makes training more stable, and it speeds up the convergence process. Okay, so once this cell has finished running, I'm going to create a new code cell, and now we're going to further pre-process our data. So I'm going to say train generator is equal to train gen.flow underscore from directory. Okay, so now I'm going to say quotation marks backslash content backslash train, comma again. I'm going to say that the target size of the images is going to all be 256 by 256. Then I'm going to say that the batch size is equal to 90. Then I'm going to say that the class mode is equal to categorical. And finally, I'm going to say that shuffle is equal to true. And I'm going to go ahead and run the cell. So we get about 9,605 images belonging to two classes. And of course, our two classes are malignant and benign. So basically, what are we doing here in our cell? So first, what we're doing here is that we're loading and resizing the images to 256 by 256. And the reason for that is because every single image in our dataset needs to be the same exact size. Next, we say that batch size is equal to 90. Now, this basically means that we are batching our images into groups of 90. Then basically, we are assigning labels as one-hot vectors, for example, 1, 0 for benign, and 0, 1 for malignant. Then we say that shuffle is equal to true, which randomly shuffles images after each epoch, crucial for generalization. Okay, so I'm going to be creating a new code cell. I'm going to copy this, paste it, and rename all the train stuff to test. And then I'm going to run it. Now basically the code over here applied all those pre-processing steps to our train folder. But now we need to do the exact same thing for our test. Now one thing to mention right now is that we are using transfer learning. And so during transfer learning, you want 80% of your data to be the train folder and around 20% of your data to be a test folder. Now this is a rough estimate and is a general rule that you want to follow. And we can see that our data kind of follows that rule, which is good. Okay, so the time has come for us to actually build our model. So I'm going to create a new code cell. And before we actually start writing some code, I want to expand on what exactly is transfer learning. So instead of training a model from scratch, which requires millions of images, we use a pre-trained model called Inception v3 that already understands how to detect features like edges, textures, and shapes. So now that we know exactly what transfer learning is, let's apply it. We're going to say from TensorFlow.Keras.Applications.Inception underscore v3. And I'm going to be importing the Inception v3 model. So I'm going to say base underscore model, and I'm going to say Inception v3 parentheses weights equals quotation marks image net, comma, I'm going to say include false or include top is equal to false. And then I'm going to say the input shape is equal to 256 by 256 by 3. And I'm going to run this cell. So we get an error, Inception v3 got unexpected keyword, wait. So this should actually be wait. We're going to run this and should be good. Okay, so now let's explore the meaning behind this code. So weights dot equals image net basically means that we are loading our Inception v3 model. Include underscore top equals false basically removes the original classification layers because we're going to be adding our own. And then input shape equals 256 by 256 by 3 specifies the size and our color channel. Okay, so next up we need to freeze the early layers of our model. So I'm going to say fine tune underscore afterwards, and then I'm going to say equals 270. Then I'm going to say for layer, and then in base underscore model dot layers brackets colon, and then copy and paste this. Create another colon and say layer dot trainable is equal to false. And I'm going to run this out. So basically what we're doing here is that we're freezing the first 270 layers of our model, allowing only the final layers to adjust to our skin lesion data. Now the reason we're doing this is because we are applying transfer learning, and this keeps general features intact while we allow the model to learn domain-specific patterns. Now if you wish, you can play around with this number, but I'm going to keep it at 270 for now. Okay, so next up we need to add some custom classifier layers to our model. So I'm going to add another code cell. Now before we add those layers, we are going to have to make a few imports. So I'm going to copy and paste them. And so these are all the imports that you're going to want in your code. Okay, so I'm going to start off by saying that gap underscore 2D is equal to global average pooling 2D, and then parentheses. Okay, so what are we doing here? Well, global average pooling 2D is a layer that takes all the feature maps from Inception v3 and turns them into a single vector by averaging each one. Now this is because Inception v3 gives us a lot of information, and so this layer will simplify it into smaller, more useful form before passing it to our dense layers. So now let's actually create our first dense layer. I'm going to start off by saying dense1 is equal to dense 800, then I'm saying the activation is equal to relu, and then finally I'm going to say that the kernel regularizer is equal to, let's say, L2, and then 0.001. Okay, so why exactly did we choose 800 neurons? Well, we want this layer to learn complex patterns in the data. Since it's the first dense layer after the base model, we give it a high number of neurons so it has enough power to learn those patterns. Now, ReLU is used to add nonlinearity, which means it helps the model learn more complicated relationships. And then finally, L2 regularization helps prevent the model from memorizing the training data. It slightly penalizes very large weights. And this is used to prevent overfitting. Now, overfitting is when our model does very well on training data because it's perhaps memorized it, and then does very poorly on our test data. So next up, I'm going to add a dropout layer. I'm going to say dropout 1 is equal to dropout 0.2. Now basically this turns off 20% of the neurons during training to make sure that the model doesn't become too dependent on any one part. Again, it's a simple way to help prevent overfitting, just like L2 regularization. So now I'm going to create our second dense layer. I'm going to copy and paste that, and I'm going to switch this to dense 2, and I'm going to switch this to 300, and keep everything the exact same. Now in our second dense layer, we only have 300 neurons. And this is because the first dense layer already extracted most of the complex patterns. This layer refines that information and helps get closer to the final prediction, but we don't need that many neurons. Finally, I'm going to say dropout 2 is equal to dropout 0.2 once again, and this is again to prevent overfitting. Now finally, I'm going to say that prediction is equal to dense 2, activation, and I'm going to say softmax. Now what exactly does this mean? So basically this is the output layer. It has 2 neurons right over here, and 1 for each class, benign or malignant. Now the softmax activation turns the output into probabilities. For example, if the output is 0.8, 0.2, that means 80% confident that the image is benign and 20% that it is malignant. Now finally, we're going to put it all together. So we're going to say model is equal to sequential. We're going to do parentheses, then bracket. And then I'm going to say base model first. Then I'm going to say our gap 2D layer. Then I'm going to say our dense 1. Then our dropout 1. Sorry, for a new cell. dropout 1, then our dense 2, then our dropout 2, and finally our prediction. Okay, so basically we're stacking all the layers into one full model. Inception v3 to extract the features, and then of course our custom layers to make the final decision. So we can go ahead and now run this cell. Okay, so finally let's compile our model. So first I'm going to import some stuff we need. We need accuracy, early stopping, as well as pickle. Okay, so now I'm going to say that model.compile, parentheses, then I'm going to say optimizer is equal to Atom. And so Atom is a good all-around optimizer that adjusts itself while training. Then I'm going to say our loss is equal to categorical underscore cross entropy. And categorical cross entropy is the correct loss function since we have two output classes and use one-hot labels like 1, 0 or 0, 1. And then finally, our metrics is going to be accuracy. And we're actually going to put this in brackets. And so accuracy is a metric we want to track to see how well the model is actually doing. So we can go ahead and run this cell. Okay, so just a few more steps before we're actually done. I'm going to add a new code cell. And this code cell is going to be used in order to implement early stopping. So I'm going to say from TensorFlow Keras callbacks, I'm going to say import early stopping. I actually already did that here, but why not do it again? So now I'm going to say that ES is equal to early stopping. And then I'm going to do parentheses, monitor equals val underscore accuracy. Then I'm going to say that the mode is equal to max. Then I'm going to say patience equals 2. And then finally restore best weights equals true. Okay, so this basically watches the validation accuracy during training. Now, if the accuracy doesn't improve for 2 rounds, basically our patience is 2, then it stops training early. It also brings back the best version of the weights, which we do right here. So before the model actually starts to overfit. So we can go ahead and run the cell. We get invalid syntax. Got an unexpected argument, patience. Spelled it wrong. Okay, so now let's actually train our model. I'm going to create a new code cell. And I'm going to say step underscore size underscore train is equal to, let's say, 105. Then I'm going to say step underscore size underscore test is equal to 10. And then I'm going to say run is equal to model.fit, parentheses. And then I'm going to say train generator, comma. Then I'm going to say steps per epoch. And I'm going to set that equal to our step underscore size underscore train, comma. Then I'm going to say that the validation data is equal to test generator. Then I'm going to say that the validation underscore steps is equal to step underscore size underscore test. Finally, I'm going to say that epochs is equal to 5. Okay, so basically we are training the model for 5 rounds, otherwise known as epochs. Now, each round processes all 9,600 training images in 105 batches, 90 images per batch, which we defined earlier. The model also checks how it's doing on the test data, which are 1,000 images in 10 batches. And so we can go ahead and run the cell. Okay, so my model has just finished running, and so let's break down what all this data actually means. So our accuracy 0.9095 represents the training accuracy for one epoch. Now I do want to point out the reason why it starts off so high is because when I first ran the cell, I had to pause it and then I re-ran it. And that's why my accuracy starts off so high. Even if your accuracy starts out pretty low, it should reach its peak at around 90%, which is also my peak. Now your validation accuracy matters more than your training accuracy. Finally, your loss should be going steadily down in both your training and your validation. Now if you want, you can run this for more than 5 epochs. I just chose 5 because I thought it would be a pretty good number to start with. But you could even try 8, 10, or 9 and just play around with different numbers and see which one gives you the best result. Okay, finally, let's print the final accuracy of our model. And this is the accuracy that really matters. So I'm going to start off by saying scores is equal to model.evaluate, parentheses, I'm going to say test generator, comma, steps is equal to step size test, and then finally print scores. Let's run this and see what we get. Okay, so we got over 88%, which is actually pretty good. Now feel free to play around with this epoch's number or even these numbers and try and see if you can get a higher accuracy. Okay, so that pretty much sums it up for this video. If you guys enjoyed it or learned something new, then please hit that subscribe button down below. Feel free to leave a comment or even hit that like button. Thank you all for watching, and I hope to see you all in a future video.